Hey, AP Calc. When I tried to understand E for myself, I needed to look at videos. And so to present it to you guys, I decided I'd make my own Mr. Nadeau-esque kind of video. So first, I just have this image of the letter E, which we also know is the number E or the mathematical constant E. And E is the base of a natural logarithm, which might not mean anything to us right now. I mean, we know that it's understood to be there in a log, but I don't know if any of us know why or what its function is. So we're going to go into that. Like pi, E is a necessary value that's the base rate of growth shared by all continually growing processes. So when you're talking about circles, for instance, their area is always going to include pi. This is a constant regardless of the circle's radius. Similarly, with rates of growth, E is always going to be a part of it, and that's what makes it a constant. All rates of growth are a scaled version of E, which is its common rate. So first we're going to talk about bacteria. And the image we have here is what we can call a simple growth rate, meaning that all of the change happens at the end of the year according to the formula. So say each one of these periods of time is 1 year. So this is 0 years, 1 year, 2 years, 3 years. At the end of 1 year, what we started with has doubled. At the end of 2 years, what we had at 1 year has doubled, and it continues like that at 3 years. When you're looking at this, you can see kind of a staircase image, meaning that you start at 1, and then all of a sudden you have 2, and then all of a sudden you have 4, and then all of a sudden you have 8. With this kind of image, the implication is that all of the growth happens at one time. But what we know to be true is that that's not the case. This power of x is the number of periods of return. And over here we have the word return, and that just means the growth rate. Another way of understanding the periods of return, which we said was x, is how many times you would double or triple your population. And is, of course, whatever your situation prompts you to do. Now let's look at a closer view of the bacteria. And what we did here is we made the time intervals smaller. So before we had 1 year, 2 years, and 3 years. Now we have like a quarter of a year and a half of a year and 3/4 and a whole year and then 1 1/4 of a year. These smaller time intervals make it possible to kind of start to see compounding continuous growth. And what this means is that we see the growth as something that's gradual, which is another term for something that's continuous. So it's not that you go from 1 bacteria to 2 right away. You can see the growth of the second bacteria from the first one. And that's more akin to what actually happens in nature. We can also see such a situation with populations or radioactive decay and interest calculations. Bacteria are different than some other situations, though, in that they cannot start multiplying themselves until they've fully grown. Despite this, though, our formula is going to stay the same, so we don't need to take that into consideration. But if we want to understand this value of E and these growth rates that are continuous better, it really helps to look at banking situations and when you put money in a bank and it collects interest. So here we have a few different graphs, but they actually end up all representing the same situation. And money is different from bacteria because it doesn't need to mature before gaining interest. And that's going to play an important part here. The development from this graph, which is we're going to call graph 1, to the final graph, which is graph 4 in this right-hand lower corner, shows what looks like a jagged kind of staircase setup, like we mentioned before, can be estimated to E, actually, which is what it represents when we put smaller time intervals. So in our first graph, we start with $1 and it becomes $2. That's kind of like before when we started with 1 bacteria and it became 2 bacteria. So we have a start and an end, but no idea really of how we got to that point. Second graph goes a step further and we divide the time interval into 2 different time intervals, meaning that there's 50% growth between each subinterval rather than 100% growth all at once. And then we can see, okay, so first we had $1.50 and then we got $2. We didn't just jump from $1 to $2. But this graph is still not completely accurate because, like we mentioned, with money, you don't have to be fully grown before you start collecting your own interest. So this 50 cents here can begin collecting its own interest as well, and we've neglected that in this graph, which is why we look at graph number 3. So in graph number 3, we see we have a $1 here and then $1.50 here, which we mentioned before. But because this 50 cents has the possibility of gaining interest, by the time 1 year has completed, which is 12 months, we have $2.25. So the growth in this equation is represented by 1 plus 100% divided by 2, so half of 100% squared, rather than 1 plus 100% squared. And that just really means that the periods we're looking at are 50% growth. And we get $2.25 there. Still, though, we can get more specific, and that's what we're doing with our fourth graph here. And this is where we can really see compound growth. In the 3 sections, there's 33% growth for each of them. And because we're compounding the interest more frequently, the total becomes $2.37. The original dollar is earning interest on itself, and its interest is earning interest, and so on. And that's what we're seeing here, this sort of buildup of interest, gaining interest, gaining interest. And the intervals are between 0 and 4, between 4 and 8, and between 8 and 12. So that's why we said there's 3 segments. When we have 3 periods of growth, the equation is going to change a little bit, and it becomes 1 plus 1/3 of 100%, all of which is to the third, because there's 3 segments, 3 periods of return, because we mentioned that the exponent represents periods of return. And when you plug your values into this, so 1 plus 1/3 of 100% to the third, you get the $2.37 that are exhibited by the graph. So if you're looking at this, you're going to say, okay, so if I compound my interest more frequently, I should continue to make more and more money. And that's our question right now. Will our returns approach infinity as we continue using shorter time intervals? So, like Mr. Nadeau often does, I'm going to give you guys a second to think about that. And if you were at home, I'd say pause the video, but you're not. So just think for a second, and I'm going to go to the next slide, and I'll show you the answer. Okay, so this equation kind of represents the question we were asking. So we have this limit as n approaches infinity of 1 plus 1 over n to the n, which equals e. And this one we should be able to recognize because it's like the 100% from the original equation we discussed. And here we have a chart kind of different n values that we plugged in to test our hypothesis or our question as to if we will continually gain more interest for smaller time intervals or more time intervals. And we can see at first we're going to make more money, but eventually toward the bottom area over here, it all seems to level off, and that's at 2.718 approximately. We hear leveling off, it should sound familiar because we are talking about a series that converges. So it relates to some stuff we're working on now. And this 2.718 value is actually E. Here you have 100 up to 1,000,000. That should make sense because we put really big numbers in to see how it would act in the most extreme scenarios. The reason this happens is that with each step forward, as we saw with the graph, we're creating this dividend that's starting its own growth, and that process is continuing. But as you create dividends, for lack of a better way of describing it, the dividend of the dividend becomes smaller and smaller and smaller, so that eventually the change in them is extremely small. And that's why you're leveling off or reaching this value, because the difference between them now is just not making much of an impact on the situation. And this converging at E, the rate of growth if we continually compound 100% return on smaller and smaller time periods. So that's how we're getting this leveling off here. And we mentioned that the 1,000,000 represents like 1,000,000 time intervals or spaces. And then this 2.718 non-repeating decimal is the maximum possible result when compounding 100% growth for one time period. If we looked at other situations, like if we had started with $2, then we would approach like 2e. Or if we started with $5,052, our answer would be 5,052e. But this e is a universal constant that's always going to play a role and be important. So I think that's enough for today. And if you have any questions, I'll be happy to answer them. And I hope this helps you understand E in a way you might not have thought of before. Stay classy, AP Calculus.